and space customers for communication, radar and EWS system development through virtualization and digital engineering. Prior to that, he was a research consultant at GE Global Research before joining Ansys, and he is PhD from Cochin University under Dr. P. Mohanan, and he has got around more than 20 publications. And I invite Mr. Nijas to deliver the talk on electromagnetic simulations beyond imagination. Thank you.
Thank you, Thomas Wood, sir. It's always a privilege to be here. And always when you come in this podium, right, your heartbeat will keep increasing because you are going to give a talk in front of your professors and friends and colleagues. So my name is Nijas, completed in 2009 MSc, 2015 PhD, then GE plus Ansys. And my mentor, my guide, my teachers, everybody is here. Happy to be there. So I'm going to cover something like Mission Impossible videos, right? Movies, something like a lot of animations. Just see everything from the top view. All the presentation which you had some time back is component like antenna, absorbers and everything. Now we will see something on practical applications. What you are doing research, how industry is using those and creating their entire product and realizations in simulation world. So these are very well-known thing. People used to design waveguides. They used to design metamaterial, filter, amplifier, isolators, antennas and different things. And simulation become one of the important and mandatory steps now, right? Before a simulation, now no company is going to build a prototype because microwave is one thing, it's not visible what is happening. Somebody has to see through the fields and check how it is, fields are propagating, whether you are getting the right gain, all those things. So we do all this kind of simulation before the fabrications. And you might have seen this wireless power transfer. Suma was talking about why they stopped wireless power transfer for health application, because the moment you are transferring power, your body will get heated up. Why? The electromagnetic energy will generate a lot of RF dissipation, which will turn into heat. So this is very important. RF and thermals are very well connected. This is one example. We designed one digital beamforming sessions, the systems where it can generate a beams to multiple users. The problem is that there is an antenna here, and each antennas are connected with the RF front end system. Those RF front end system is the one which control your beams and do signal processing. And these all signal will go to a processor where all the beamforming will happen. But there are some kind of RF power amplifier, LNAs, mixers and other components which are power hungry. So what will happen is when you do a analysis, you can specify I'm going to use this much of power for each component. Then you can predict what will be the temperature going to generate. The temperature for without any heat or thermal adjustment, the temperature was 335 degree. So everybody knows that if it goes to 335 degree, your PCB will get melted. Your components will just float on the PCB and it will get burned out. First thing what people will do, they will use heat sinks. So I can use heat sinks, the temperature reduced to 235 degree. Still it is not sufficient. You need to bring the temperature down. You can add external fans. So heat sinks with external fans, it reduces the temperature to 130 degree. The third option is, if the 130 degree is also not sufficient for you, what you can do, you can add a liquid cooling. So people can use a liquid which will go through all the PCBs and come out. So chilled water or chilled, that's called a glycol liquid, which is very thermally conductive and electrically non-conductive liquid. That will pass through this pipe and goes all the way and come out here, which reduces to 174 degree. Then if you see this particular PCB, there is actually this area power amplifier sits. Power amplifier is the one in that RF front end will consume a lot of power, and that will heat it up. So what happening is these pipes which we are connecting is actually in the back side of the the PCB. So the power amplifier is heating here, but temperature is not coming to the back side. So what we can do is you can add a kind of a thermal vias on the PCB, which will take the temperature from one side of the PCB to the other side. So that reduces the temperature to 74 degree, which most of the military standard or space standard IC can be easily handled. Then the last option is you can immerse into the glycol liquid. That's another option. So we do these kind of analysis before you are finalizing your product, because once you design all the microwave system, beamforming systems, the thermal management is also very important. Otherwise, within 5 minutes, your entire system will burn out. Okay. So these are some of the analysis. I mean is sometimes you need to go beyond electromagnetics, because when the electromagnetics works with the network analyzer goes well, but most of the practical application it generates a lot of heat, so you need to have a thermal mechanism also to adjust and stabilize it. So this is very common. We do a lot of antennas, and I know we have that photolithography room. We just create 10-20 antennas every weeks. Out of that will go something to publications. After publication, what you will do that antennas, right? So all these academics, where CUSAT and IITs and all the foreign universities, people invent a new type of antennas, and all the industry people are keen to see what kind of antennas are coming from research. We normally refer all these IEEE papers and identify which one is best, where I can use it for my applications. So this is a kind of antenna we do, and a lot of type of antennas. Now when it comes to your mobile phone, laptops and other thing, which consist of a lot of microwave components, which all start from the die. So this processor, right, they are very tiny one, sometimes in the order of nanometer size, but they still carry the electromagnetic waves. You need to simulate from or analyze from this point. Then this is called a package. This actually sits inside this, and this sits inside the PCB. And let's say this processor wanted to communicate with the IC. How it will go? It will go through the microstrip line. So you studied the microstrip line in your electromagnetics, strip line, microstrip lines, and you need to check whether if I send some signal from here, whether it will go into receive or here. Another one, all these antenna or PCBs now comes with a lot of antennas, because you need to have Bluetooth, Wi-Fi, all the connectivity with your device. There are some provision they will keep to place the antennas, and everything has to be powered. So there will be DC-DC converter or inverters, and this will be the complete assembly of your PCB. Talking about time to frequency conversion, frequency to time conversions, and other thing. And the second thing we normally does is the antenna simulations, right? Most of the research people here does either antenna or RCS. So if you do a lot of antennas and place it on this kind of UAV and drones, what will happen? Because it has a metallic wings, the antenna shape going to totally change. So even though you will publish a paper telling that your antenna is having very good elevation cut and azimuth cut, the moment it plays on the system, the pattern is completely changed. You need to account when you are actually going to do analysis. So this is one case where you see this, there is a blade antenna, nice radiation pattern is coming, with and without landing gear, the pattern looks something like this. So this is the ideal antenna pattern. These are the antenna pattern cross sections when it's installed on the UAV. So what you will do next? So I'm placing this antenna. Is that ending my testing? No, I need to fly my UAV through some area, and I wanted to see whether I am able to communicate with that. How we will do that testing? You need to have a UAV, you need to fly it. There are simulations now possible to do that in completely in virtual way. I'll show you one video. This is in a India-Pak border. So I can model the entire universe in a simulation tool, and you can see all the mountains, everything. There is a drone, there is a ground station, there is a jammer also here. The same UAV with the same installed antenna pattern working at 1.2 gigahertz is now flying over my virtual world. Then this is my UAV. I can set where I need to place my ground station. So my ground station is here, which is actually transmitting 1.2 gigahertz. But what I did is, since it is a border area, there will be some enemy jammers or interferer which trying to jam your communication. I can place it wherever I want, and I can also tell how much power I am pumping from the jammer. Now I am going to fly my UAV. What you are seeing is a signal to noise ratio. The green one is indicating without jammer, and this one is indicating with the jammer. And you can see the moment the mountain was earlier blocking, that is the reason here it is same. The moment mountain start block, like there is a line of sight established between jammer to UAV, you can clearly see your signal to noise ratio is going down. Now I can identify with my antenna after I place my UAV. If I go for a mission, a virtual missions, how my communication going to establish? This is actually the 0 dB. So these area I am going to lose my communication with the ground station, but I will get established again. So most of the time we actually end up with the antenna simulation, but for companies like the UAV, drone or aircraft, any companies, even telecom also, they want to test something like this. Flying and testing in actual world will cost so much of dollars, and this can be done it in a laptop. Actually I run it on this particular laptop, and you can see because of mountain there is no problem at these areas. So they can, sometimes the defense people actually run this analysis and they will optimize the route. Okay, if I do another route, can I get rid of this jamming? So another case, in order to have a communication, yes.
So this was STK.
This is STK with HFSS, yeah.
So the previous topic that you were discussing about this PCB,
Pure HFSS.
so how you are importing the PCB layouts from some other like web files or something directly into
Yeah,
Ansys, and then you are simulating.
correct.
You don't have to recreate it.
No. There is a seamless workflow is available. You can import the PCBs and then do it. And this is with the mission analysis. This is we call the digital mission engineering. All the virtual route will create in SDK. So I'm not talking about any software here. So Ansys is promoting a lot of academic. I can guarantee all these tools which I am going to present today is available under Ansys academic program. It's a lot of software, but I don't know how many people are going to use it. So if you want to have a communication from one point, if I wanted to communicate from here to Niraj over my digital phone, I wanted to send photo. So those are digital data, 1010 bits, right? And if I send, I need to convert that 1010 bit into my higher frequency, let's say 100 megahertz. Then I will up convert that into, let's say 3.5 gigahertz, which is my GPS, or maybe 2 gigahertz for my LTE carrier frequency, and send it to base station to again Niraj. Niraj will down convert it again into 100 megahertz and convert it into digital section. So everything can be modeled as a block by block here. So you can see my digital signals, my digital front end, my RF front end, my channel is nothing but I have a UAV, I have a ground station, I have a ship. UAV is flying over the sky, ground station and ships are in different locations. So I need to know what is a path loss, free space loss, right? So phase transmission method can be used. I can calculate, and I have a receiver side ground RF front end. I have my digital demodulators. So I can integrate all these blocks with a lot of simulation, measurement data, some vendor data, and finally I can see something like this. I can fly my UAV and I can see at what all time. This is much more advanced than what I shown as earlier. Now you can see I lost my communication with the ship, but since it is a beamforming system, it re-established very easily. And you can see it taking a lot of maneuvering, and going and coming, and every time I can check how much is my transmitter power, how much is receiving in ground station, how much power is receiving in my ship. So these can be dynamically check it and see whether I made a system going to work in real life or not. Not only that, if you see, till now I mentioned everything was on simulation side, right? And there was no product. So if somebody is designing, this is called LRUs, or a device which is actually generating your RF microwave. I can connect that to the hardware, and then this can be placed on a UAV or a satellite or anything. So how to test it? They need to take this device into your aircraft, fly it, and then check whether the communication going to establish or not. So we do what we do. This is connecting with the NI system, and this same simulation I can connect with the NI and see hardware going to work or not. So this is an example where there is a satellite and ground station. This is connected with the NI hardware. So if I click one more time, you can see this satellite is moving. My constellation diagrams are perfect, but as it goes away, I am going to lose my communication because the distance is become ground station to ship become very high. And one point you will see, this is actually the transmitter board. This is actually it's called the emulator. Now I am going to lose my communication. So simulation helping a lot of customers rather than doing an actual flight test. You can create a flight test in simulation and connect that to the hardware and see whether your designed product going to work or not. Another interesting thing, okay.
So I cannot disclose much because of the confidentiality of the client and all that, but you have an aircraft and you have certain antennas that you have tested out without the aircraft. Like basically, I'll tell you, it is direction finding system basically, amplitude comparison direction finding, and using machine learning to do that. Now, this direction finding system, if you do it on its own, like the patch antennas are on their own, no issues. You can train your algorithm and it works perfectly fine. But the moment you deploy these antennas onto the helicopter body, the shape of the beam changes completely, and this whatever algorithm you trained would no longer work.
Your face is going to change.
Yeah, this is very cool thing that I saw, where can you import 3D geometry of an aircraft inside STK itself completely, and then mount these antennas, and you can have this radiation pattern being simulated there, and then with this NI Pixie system and all, you can actually have real signals coming in. Is it possible
you can
to do that setup?
So there is already one test setup is done in ADE Bangalore.
Okay.
Now I'm working with the DLRL for exactly same top.
Oh wow.
We can discuss parallel.
Okay.
So have you seen this video anytime? What is that? Huh? SpaceX re-entry happening. And what is this glowing stuff? Somebody putting light in hypersonic speed. This is actually the plasma getting created. So when you're flying at very high speed, this is flying at 25,000 km/h. That means almost like a 25 Mach speed. Mach is nothing but Mach 1 means speeding at the same speed of sound. Mach 2, it goes tell 2 times of your speed is 2 times of the sound speed, right? So this is flying at 25 times of sound speed, and that time what will happen? The friction between your aircraft body and air going to generate a lot of heat, and air became plasma. So this is the plasma visuals. Earlier nobody were able to see these videos because by the time the plasma generates, everything will be blacked out. No, means this entire aircraft will get blackout and no communication going to establish. So Starlink established that communication even during the plasma generation time. So this is how this is how it will look like. This is for Starlink. This is for all the re-entry application. Now ISRO is going to send us a Gaganyaan mission that will exactly look like this. This is a NASA Oryx capsule, and the plasma generation for this will be something like this. So couple of customers, especially aerospace and defense customer, came to us. Can you tell us how the plasma going to generate and whether your antenna going to lose the communication or not? So if you see this particular graph, this is an interesting graph. It is telling when this is the altitude and this is the time. So when the altitude become 80 kilometer to between around 50 kilometer, there is a blackout time, because air density become very high during that time and your speed is very high. The plasma will be very, very large and you are going to block your communication. The plasma is nothing but the air became ionized, lot of electrons. Assume there is a air with a lot of electrons, it became conductive, right? It's blocking your entire antenna with a conductive layer. So something like you are putting antenna and you put antenna efficiency, we do Wheeler cap method, right? Something like that. You are enclosing everything with a plasma region. So we created a workflow for those people, and there's a crazy things. 2022 US developed this workflow, one of my team member, but they told hypersonic is very confidential thing, it cannot be shared outside US, it's a classified informations. So then my team along with 2-3 people, we created a workflow. What we do is we do CFD simulation. CFD stands for computational fluid dynamics, where you can set the speed of your vehicle, then it will calculate a couple of quantities. I will come to that one, and this quantity can be converted into permittivity and conductivity. So if you do use a simple Maxwell equations, you can convert this into permittivity and conductivity, and then you can check where your antenna going to radiate or not. Okay, I'll just go through this one. So this is actual flight test data. This is telling that your aircraft is going at 27 max speed, means 27 times faster than the air speed. This is how your speed, because different area in the body will have a different speed, air speed, and this is called electron density. So when the plasma generating, this entire area become highly electron, means it became conductive, these areas. And this is a flight test data, and we just tested with our simulations coming quite well. Then what we did is, without any plasma region, we created a 3 antenna, one working at 300 megahertz, 1 gigahertz and 1.8 gigahertz. We found antennas radiation patterns are something like this, perfect. Now I wanted to see, when I going to keep these antennas on plasma environment, when the re-entry going to happen, which all antenna going to work. So there is a nice expressions which is connected with the number of electrons, number of mass of the electron, temperature of the electrons. Then it will calculate plasma frequency. Plasma frequency is connected with these quantities, and your permittivity and conductivity is connected with this is called collision frequency. So your material property going to change across the frequency because of these expressions. And from CFD, fluid dynamics data, we will get this data, then you can convert it into a simple permittivity and conductivity expressions. We take that data. So for example, we did 3 simulations. One is at 96 kilometer, which is just before the blackout time. Then another one is during the blackout, then just after the blackout, how the performance of the antenna going to be. So this is the 96 kilometer height, 300 megahertz. You can see, check about this. This is actually negative permittivity. This is creating a metamaterial environment when the plasma is getting generated, and that is changing with respect to frequency a lot. So for example, this is nothing but attenuations, alpha, and alpha is telling 300 megahertz is attenuation is very high around the capsule. This is almost like 10 kilometer by 6 kilometer area. At 1 gigahertz it's reduced, and 1.8 gigahertz it's further reduced. So that means if I use a higher frequency antenna for communication, I can still use. So if I, instead of that, if I use 300 megahertz, 96 kilometer itself, I will lose my communication. Now if I use this 300 megahertz, my ideal antenna was 4.4 dB gain. With 300 megahertz antenna, my gain is very, very negative. Means the plasma environment is completely blocking my radiations. This is at 1 gigahertz, is still very low. You can see the plasma is wherever there is a small area where there is no plasma, and you can see only that area the electric fields are there. The remaining area is actually blocking by the fields are blocking by the plasma. Another one, sorry, I'll just go very quickly. This is even at the 6 dB is the gain, but with the plasma gain is still positive. That means you can still establish the communications. At this is the area actually the blackout going to happen. Okay, when that area comes, whether you use 300 megahertz or 1 gigahertz or 1.8 gigahertz, there is no communication going to be, because attenuation is too high during this frequency. We did a couple of computation up to 20. If you go 25 gigahertz and above, you can still have a communications. The problem is that time your Doppler frequency shift plus the attenuation is going to increase over the frequency, right? Phase transmission equation, if you see, is connected with the lambda. As you increase the frequency, the same distance, your attenuation going to be very high. So that there is a challenge. So at this frequency, there is no radiation, minus 762 dB gain. There is no radiation is coming out. Even at 1.8 gigahertz also there is no radiations. This is the frequency at which we came out from the blackout area. You can see at the 40 kilometer there is no attenuation here, so your antennas are starts working perfectly, but slight variations because of the still there is a small material property variations. So this is some physics where people never thought simulation can help them, which came to us 4 or 5 defense labs. They were telling this is an area, can you work? Somebody started working 5 years and they told it's not getting. We tried to crack that one, and this is one of our this year effort to create a workflow for this application. Now there was a Krama lab. So far I covered Krama lab. Now I am coming to RCS labs for you, Anand sir. So we'll talk more about RCS now, RCS and radar. There are people, and still people design radar absorbers. Who all are there working on the radars here? Good. So the radar, when you create absorbers, right, this is also going to use some part of the aircraft. Sometimes it may not be possible to use for every part of the aircraft, but some part where the RCS are high, they will try to add that absorbers. So a couple of analysis we do: RCS, bistatic, monostatic, range, waterfall, ISR images. RCS is a part like function of a geometry and shape, size, frequency and all. Whether you change your shapes, your RCS is going to change. Created a toolkit with development and created 2D, 3D RCS images. And you can also visualize when the wave is coming and when the wave is coming and hitting in this aircraft, how the how the scattering going to happen. So this is how the field going to scattered and reflected back. So if you see this RCS of this aircraft, they wanted to see there are some peaks which is coming across the different angle. If I want to identify which part of the aircraft is generating that RCS, I can do an ISR image and tell, okay, at this direction, these engines are actually creating the high reflections. At this particular angle, these engine is creating issue. But you see there is a one peak here, which is actually causing by the fuselage of aircraft. So you can identify which area of your object is creating RCS. And what people will do, they will actually implement these radar absorbers around that area. Okay. There is stealth technologies are coming. The people are earlier used to do monostatic RCS or imaging method. Now people are going to do bistatic, where your transmitter antenna will be somewhere else. And why this is not going? Okay, so your transmitting antenna is here, your receiver antenna can be anywhere, because stealth technologies reduces the RCS of the aircraft too much, but still I wanted to detect it. What I will do, I will transmit from here, radar, the aircraft will be somewhere else, but I will have multiple receiver aircraft across my area, and all things are synchronized. My time, my radar receivers, everything synchronized. Then that technology is called bistatic radar technology, which can create images, which can even dictate a stealth aircraft. So we do that part also. So the imagination actually stops. The simulation gives you wings to go anything and do everything in the simulations, right? You just do a control set, it comes back. That's the reason. So this is a one case where and radar. So far we discussed about RCS, ISAR and everything. Anybody have seen this automotive radar? Now every car is coming with a radar, right? Automatic braking, it detects speed of the front vehicle and detect it. This is actually the data from the radar looks this. You will see there is a detection, there are some strong signals. This is how it will tell. It never going to tell you what is the shape of your detections or anything. It will give you something called velocity. It also will tell you what is the distance I am detecting. So radar velocity, directions, whether it is positive Doppler, that means something is coming towards you. If it's negative Doppler, something is going away from you. Then it will also tell at what distance you detected it. Okay. This is another example. I have a radar. Oops. I have a radar here. Then, come on. Yeah. So there is a tank actually moving here, right? So in the beginning you will see this is a velocity, this is a positive velocity, now it is going into negative velocity. Why? Something is going towards you. At the beginning it was coming towards the radar, then it was positive velocity. Now it is going away from the radar, it turned into negative velocity. This is called clutter from the terrain. And there is one more tank which you can detect here. This is that tank. And that detection, when you see this automotive radar or defense radar, this is how your image will look like. There is something called a synthetic aperture radar, which is instead of doing one pulse, I can do multiple pulse for different time, and then I can create something like a coherent summations and do some post processing. I can create something called synthetic aperture radar. People might have heard about specific absorption rate. So there is something called synthetic aperture radar also. So this is a measurement of that Denver stadium. This is the Denver stadium in US, a very big football stadium. And what you all need is a CAD model of this stadium. This is stadium where you just assign, like in simulation, what is the material property, conductivity, permittivity and everything. Then this is the measurement and this is the simulation data. So measurement is actually did by a company called Capella Space. It's a US company. What they did is they put everything in their aircraft, the radar, everything, flew it and spent millions of money, generated this image. This is on the laptop. I can create it. If I have a model, a CAD model of anything, I can create an image which is exactly generate a simulation and measurement. But you see there is a lot of roads and another thing which is not there here. Actually it is there because in measurement a lot of phase noise, broadband noise will add up. This is actually covering, blocking because of those noise. But you see there are few roads, you can also see from here. So simulation is give you a wing to check whether your system going to work or how the algorithm has to be designed. Not only that, on a simulation I can rotate it and see with if aircraft is flying at a different path, how my image going to be. This is, you might have known, India Gate, Red Fort, Qutub Minar, Charminar, Konark Temple, Lotus. If I do these SAR image of it, it will look something like this. Oh, sorry, I'll just flash it. Oh. I'm sorry, some issue on my side. Yeah. Okay. Last two slides before my completion. I don't want that. It's fine. Just wait for a few seconds, it will play. This is the actual CAD model of each monuments, and you can see this is how the SAR image of each one look like. Okay, so where I can use it now, lot of defense company we are working, they wanted to see if somebody parked some civilian aircraft, military aircraft, or as consider a seabed where I have a shipping boat, I have a commercial boat, I have a destroyer, I have a flight carrier. So such aircraft or ships are there. There are algorithms they are developing. So the AI based algorithm. AI based algorithm, the good thing with AI is without training data, AI is a big zero. So you need to have a lot of data to train your AI that okay, this is your destroyer ship, this is your fighter aircraft. So for example here, this is a Paris city, right? This is a Paris city in France. One second. It's my last slide. And you can see the SAR image of that Paris city, and you can see there are two ships. I kept it. Now you can see that two ships are detecting over here. So even though optical image will be different and radar image will be different, but radar having a lot of advantages. Whether you do fly your aircraft or satellite, LEO satellites in day or night with the cloudy or rainy situations, you still get pretty good images. And you can also see I kept a few 9 small Cessna aircrafts. You can see those Cessna aircraft here, you see. And this is how people can create a lot of training data using simulation. And you won't believe these simulations, I can run it in my laptop almost like a real time. So I can place my radar on satellite or aircraft or ground station and see how a flying aircraft image will look like, how SAR image will look like. If there is a satellite is flying on the sky, I can check from ground station and see how the satellite image from the ground will look like, because there is about 10,000 plus LEO satellites are there in the sky. So with that, I am concluding my presentation. Any questions? Welcome.
Sir, first of all, I really appreciate the effort and the hard work behind each scene. And my question is that in deep space communication, what are the precautions taken for? Because the objects such as satellites are millions of kilometers away. There must have a proper low noise amplifier such as crypto. So we need a cryogenic systems for that. So what are the main precautions taken for receiving very faint and weak signal from deep space?
Okay, first of all, I'm not the expert in the deep space area, but I used to work with ISR a lot. Okay, from that what they do, they have a very big antennas. Sometimes the dish antennas, you know, right? It will be like couple of meters in big, but they even create sometimes an array of dish antennas, which can create even bigger gain. That's one way, increase the gain of the antenna systems. Second one they can do is a relay. So many communication now happening not from directly to ground station from the deep space. They will first communicate with some of the satellite which may be rounding around Mars or Moon. If they can establish that communication, and then it goes to another satellite which is around maybe LEO or GEO satellites, and then it goes to one of the ground stations, and then they process it. There are multiple way they do, and very important thing is this multiple way they called this multi-hop communication method. Then second one is that the noise, the signal level is too low, and I mentioned was a noise level, right, in that RF interference case. This can be brought down by KTB, which is very difficult because that's called broadband noise. T is one of the criteria. Temperature. So they actually keep these receivers in a very chilled environment, bring down the temperature so that they can reduce the noise further. So a lot of methods are there. They will combine everything and then try to decode it.
Okay, thanks for the clarification.
whether this are images which you have shown is by using this Ansys simulation you have done?
Yeah, currently I don't have any other simulation tool access, so everything with the Ansys simulation.
Yeah,
yes.
so that normal HFSS.
Oh no, there is three major computation method. One is finite element method, FTTD method, then something called integral equation method. But those are for maybe small to medium size. But SAR simulation, you see, I simulated for kilometers sometimes. So those cannot be simulated with these kind of solver. So I can use a shooting and bouncing ray solver, which is also available in HFSS. The problem with that is CPU based one. But I do have a GPU version of it. That's called one software called PercyVM. I'll show you this. This is an example of that. Where it is. Indian monuments. I'll just play this. Okay. Somehow my system is not responding as expected. Maybe because of charger. I don't know. So this is a Python based one. So if you are good in programming, you can just write all this code. The solver is a GPU based code which generate these images in real time on my laptop. If I have a very good machines, even faster, sometimes faster than real time. So there is a GPU based solvers are available. It's nothing but a HFSS SPR solver rewritten in GPU.
Okay. So you are not specifying any frequency for that?
Oh, everything. Well, you need to specify frequency, you need to specify bandwidth of your radar, everything you need to specify without any what all things you physically need. You need to have a CAD, you need to have a frequency, you need to have an antenna, everything need to be specified, then it will create it.
And also in the PCB design, you are enabling each portion separately and you are seeing whether it is interfering with the other part of the PCB, right? Initially when you are shown the slide about the antenna kept in the PCB as well as the other digital processor kept in the PCB. You are enabling it separately, right? So
no, all together.
Yeah.
So we just extract the S parameter. S parameter will tell you from my digital section to antenna section how much is the S21 or isolations, and then I can bring into a circuit simulation, give the digital signal and see how much voltage is coming in there. So there is a frequency to time one conversion will happen that circuit tools will take care.
So first you will, for example, the digital processor, you will excite it and then you check the electric field analysis, and after that you will excite both antenna as well as the digital processor, then you will again...
Here antenna is a receiver, I won't excite antenna, I'll only excite my digital section and see how much is the leakage voltage is coming into my antenna terminal.
Okay.
So this is that GPU solver. You can see this just running on my small laptop. It's real time able to solve it, and this is almost like a 2 kilometer by 2 kilometer area.
So whether this all the targets are the same area or you
I just placed in 2 kilometer by area all these 9 targets, and then I assumed my flight is actually circling around it. It's a spotlight SAR and it's generating the image out of it. So what I mentioned in these presentations, everything is there in most of your license. I think in DOE definitely will have an academic license of Ansys. All this solver, GPU solver, SDK, everything is accessible to you. So all of nothing but if you have a passion, try it out. You have everything in your hand. I think I grabbed a lot of time of your presentations. Oh, this is a X-band, yeah.
Thank you, sir. We also extend our gratitude to Thomas, sir, for chairing the session. Before we conclude the session, I like to invite Nijas, sir, to kindly accept a token of appreciation as a small gesture of our thanks. I request Thomas, sir, to do the honor.